Hi, my name is Christy Eslinger, and I'm a graduate student here at CHS. I want to talk to you the next few minutes about the challenges we've run into when optimizing the chromatin immunoprecipitation studies, or basically a chip assay. Well, the first question would be, why would you even need to utilize a chip assay? To explain that, let me just tell you about our research. So I've been using TMBS to induce colitis in rat, as you can see right here with colon C. And by doing that, I'm able to focus in and look at glutaminase or GLS1. And what I'm showing or what I'm seeing is that there's a hypermethylation taking place right in the promoter region of my GLS1, and that there's also MECP2 or methyl CpG binding protein 2 that is being recruited into this binding domain that is allowing transcription to take place, which is quite non-traditional. Traditionally, we think of DNA methylation as silencing a gene. So it was quite imperative that we actually exhibit or show that MECP2 is actually directly bound to the GLS1 in the promoter region right on the DNA. So then it was, well, what is a chip assay? A chip assay is when you take your sample and you cross-link or you fix that sample. And that way, my whole binding domain stays intact throughout this whole experiment. And then the next thing you would do is fragment your DNA. Well, fragmenting your DNA means just getting it to a particular size of 100 base pairs to 200 base pairs. And then you would put in a antibody. This is immunoprecipitation. Is when you put in an antibody that's going to bind to that protein of interest, which for me was MECP2. And then to do the DNA purification, I used the Cephros bead. So you can put in a bead that binds to that antibody, which is bound to that protein of interest, which is cross-linked and fixed to that piece of DNA. And see, I can pull down that bead then, wash everything away, do like a simple protease K wash, and then all I have left is just that piece of DNA to analyze further and look for GLS1. And what I found was pretty incredible that the fragmentation step was the most important step. Like you had to have this DNA at a particular size or it just would not give you consistent good data. And the first time I did this, I just sonicated. And I don't know if I was just holding my mouth just right that day, but it worked. It worked the first time I tried it. When I ran into issues is when I came back and I tried to repeat the experiment. I couldn't get it to work. I kept getting my DNA to less than 100 base pairs and wouldn't even show up on my gels. So then we turned to some commercial enzymes to see, could we use a commercial enzyme to actually cut my DNA to a certain size that would be great for chip assay. So the first one I tried was micrococcal nuclease or MNase. So MNase works off the precedence that it comes in and it cuts the linker DNA in between your nucleosomes or your histones. It will come in and cut and give you smaller pieces of DNA that way. But this was not consistent and it wasn't really reliable for me. It would be great, and I do highly recommend it if you're trying to map nucleosomes. Because of the way it works, this would be great for that. The next one I tried was fragmentase, which fragmentase, it works off of two enzymes. Well, the first enzyme comes in and it puts random nicks in one side of your double-stranded DNA. And then the next enzyme will come in and it will recognize these nicks and it will cut the opposite strand of DNA, giving you overlapping segments of DNA, which, by the way, this is great for sequencing. I could definitely see that if you were going to sequence that this would be a great one to use. But the protocol for this calls for a very minute amount of DNA, and we're using whole genomic DNA. So it kind of overwhelms the system, and it's just not really reliable for us either. So that left me sonication. I had to optimize and get more uniform with my sonication step so that I would know each time this is exactly what I was getting, the same size each time. So I want to show you guys real quick. When I used the MNase and I did a 1 minute digestion, guys, this is just 1 minute. You can see it gave me just above 100 base pairs. But the 2 minute, 3 minute, 5 minute, 8 minute, all these are too small. They're less than 100 base pairs, and these wouldn't even show up on a gel. And this wasn't this way every time. Like one time it would work, and the next time it wouldn't. It just wasn't real reliable for me. And then the fragmentase, as you can see, the fragmentase protocol, it calls for 1 to 5 micrograms of purified DNA. And that's not what we were using. We're using whole genomic DNA. And I'm going to estimate that I was using somewhere around 20 micrograms was used. So this didn't give us really good, reliable cutting, and it just wasn't really consistent. So neither one of these really would work for what we needed. So I fell back onto the sonication step. And what I found was that if I sonicated for 1 second on a setting of 1, I'm not kidding, 1/1000, and that's it, it would give me the perfect size of DNA each time, as you can see here. I did a chip assay where I pulled down with MECP2, got rid of everything, followed all that up with a bisulfite conversion, and then a methylation specific PCR just to show this is happening in my methylated lanes. So you can see in my unmethylated, there is nothing. There's no bands showing up. But in my methylated lane, you can see I have hypermethylation in my TNBS treated animal, and this is GLS1. And then this hypermethylation comes back down to control levels when I use a global demethylation compound called azacitidine. Of course, future direction would be that I would follow this up with an IMSA. I would also sequence the DNA. But all in all, this was very encouraging and it was a lot of fun to do. So if you have any questions, please feel free to email me. Thank you for your time, and that's it.